Welcome everyone. I'm Santosh Raikar, and today we're going to discuss circular maintenance. In our industry, we often talk about repairing, reusing, and remanufacturing as ways to be more sustainable or save costs. But there is a dangerous trap here. If we aren't careful, we might be trading away the very reliability our plants depend on. Today, we'll explore how to recover technical scope and value without compromising performance. Let's start with a scenario many of you have likely faced. Imagine a gearbox returns to your plant with a fresh coat of paint and a simple one-page certificate. It looks new, and it was certainly cheaper than a new one. But then you realize the serial number is uncertain, there are no records of gear contact or bearing clearances, and the duty requirement for that machine have actually changed since it was sent out. You've saved money on the purchase, but you've lost the evidence needed to manage reliability risk. The question is, what actually makes this asset fit for service? This matters because a circular system only creates real value when the components have controlled provenance and performance equal to the duty they will re-enter. We need to understand that not all recovery is equal. Repair and remanufacture are very different things. Ultimately, the duty of the machine must govern whether a part is acceptable. The core or used part must serve as technical evidence, and true value must be measured over the entire life cycle, not just the initial invoice. By the end of this session, I want you to be able to do 6 things. Differentiate between the types of recovery, classify components by risk, control the identity of your used parts, write technical scopes that actually mean something, qualify your vendors properly, and finally, measure the real life cycle cost of your decisions. Think of this deck as both a presentation and a practical training module for your plant. In Section 1, we're going to learn how to see the risk clearly. We need to identify the system conditions that turn ordinary maintenance work into a significant enterprise risk. To manage risk, we must use precise language. Reuse means using a part again with minimal processing. Repair means fixing identified faults, but not necessarily returning it to like-new condition. Refurbishment adds a level of cosmetic and service improvement, while remanufacture is a full industrial process to return a product to its original performance. Understanding the core, the used part itself, and its provenance or history is vital for any of these to work. The risks here are bigger than a maintenance invoice. Poor reliability can hide fatigue or dimensional damage under a coat of paint, while circular maintenance can improve availability by reducing lead times. The costs only balance out if we avoid premature failures. True sustainability only happens when the energy saved by recovering a part isn't erased by the waste of a repeat failure. Failures in circular maintenance usually happen as a chain of events. It starts with an unknown core with no history, followed by a generic repair as required scope. This leads to hidden substitutions of materials or dimensions, and finally, a weak acceptance process where a paint job is accepted as proof of quality. The result? A repeat failure. We must ensure every step is engineered and verified. We should look for the warning signs of a failing system. Core mix-ups where identity is lost, no fault found returns where the root cause is never addressed, and scope creep where the vendor makes decisions without owner approval. We also need to watch out for poor storage that damages recovered assets before they even get installed, and warranty leakage, where we fail to hold suppliers accountable for repeat issues. I challenge you to ask these 8 questions about your current system. Don't answer with what you intend to do, but with what you can prove with evidence. Do you define your terms? Do you classify risk? Can you trace every core? If you can't answer yes with evidence to these, your reliability is at risk. Now that we see the risks, Section 2 will focus on building a disciplined operating model. We need a system with explicit decisions, controls, and evidence. There are 5 principles that keep this model practical. First, duty before discount. Understand the service requirements first. Second, preserve identity. Treat the core's history as a critical asset. Third, specify the transformation. Tell the vendor exactly what to do. Fourth, accept performance based on measurable criteria. And fifth, always learn by looking at the full lifecycle performance. To tie this together, I use the RECORE 6 model. It's a 6-step process. Classify the risk, capture the core's identity, specify the technical scope, qualify the vendor, accept the product with evidence, and perform and learn from the field. This turns circularity from a purchasing shortcut into a genuine engineered asset strategy. Let's break these down. Step 1 is classify. Before anything else, reliability and engineering teams must define the intended duty and criticality of the part to decide if reuse, repair, or remanufacture is even appropriate. Step 2 is capture. The maintenance and stores teams are accountable here. They must tag the asset, record why it failed, and protect that evidence during transport. The output is a traceable core dossier that travels with the part. Step 3 is specify. A technical authority must write a specific engineering repair specification. This shouldn't just say fix it. It should mandate specific cleaning, inspection methods, salvage limits, and the exact tests required for acceptance. Step 4 is qualify. Quality and procurement teams need to ensure the vendor actually has the equipment, skills, and sub-supplier controls to do the work. We need to approve the path for any deviations before the work begins. Step 5 is accept. When the part comes back, an owner inspector must review the as found and as left reports. We check the material traceability and witness critical tests to ensure the recovered asset is truly ready for service. Finally, step 6 is perform and learn. The asset manager tracks the part once it's back in the field. We monitor the installation, link its performance back to the repair history, and use that data to improve our future strategy or vendor scores. To keep the system honest, we need clear decision rules. For example, if a core's history is lost, we must downgrade its suitability or reject it for critical duty. If a vendor proposes a substitution, it requires engineering approval. These rules prevent convenience from overriding sound engineering policy. Now, we move to Section 3, making it executable. A model is only useful if it translates into a field workflow with clear ownership and a management cadence. Reliability often fails in the gaps between departments. We need one accountable owner for the process, but everyone has a role. The asset engineer defines the scope. Maintenance preserves the evidence. Stores control the logistics, and procurement manages the vendor quality. Standard work is what makes this repeatable. We follow the RACOR, 6 steps we just discussed, but we add a 7th step, sustain. This involves auditing our own controls to ensure the standard is being followed and updated as we learn. Controls must be observable actions, not just training. We use a circular suitability matrix, a digital core passport for history, technical repair specifications, and an owner acceptance gate. Each of these is a specific checkpoint that ensures the quality of the process. Data is the backbone of circular reliability. We need to capture the minimum data that actually changes a decision, from the core's identity and as-found condition to the specific repair transformation, acceptance results, installation baseline, and finally, its next life performance. To manage this, we use measures that trigger action. We look at leading indicators like core traceability and first-pass acceptance, and pair them with lagging business outcomes like next life survival and life cycle cost ratio. If our recovered parts aren't surviving as long as new ones, we need to know why. Management cadence makes this culture durable. From daily frontline reviews of exceptions to annual strategy resets, this rhythm ensures that we are constantly closing gaps and verifying that our standards are actually being used in the field. Technology should reinforce this discipline. We can use a digital core passport to connect our EAM and ERP systems with vendor portals and condition monitoring. This provides a single, traceable history for every asset, allowing for deep lifecycle analytics. In Section 4, we focus on how to apply, verify, and sustain this method. We want to scale only after we have evidence that the process works. Let's revisit our gearbox case. The team sees a serial number mismatch, increased duty requirements, no gear contact records, and a simple no-load test. At this point, you have a critical decision. Do you risk installing it, or do you reject it because the evidence of reliability is missing? The intervention here isn't just fixing the gearbox, it's changing the system. We apply the RACOR 6 framework, classify the current duty, reconstruct the identity, issue a proper engineering scope, and only accept the part when we have the right vibration and contact evidence. Success becomes visible through specific indicators: unambiguous identity, reused parts that meet documented limits, and owner-approved deviations. The key lessons are simple but vital. Paint is not remanufacture, and the core passport is what protects your reliability. Here's a tabletop exercise for your teams. A critical motor is needed. You can get a new one in 28 weeks, or a remanufactured one in 6 weeks with limited history. How does criticality affect your choice? What evidence would you demand? This exercise helps teams practice making technical decisions under pressure. Watch out for common traps. Don't call every repair remanufacture. Don't select vendors based solely on purchase price. And never accept a no-load test as full acceptance for a high-duty part. The recovery move is always to define the process and the performance criteria explicitly. If you want to start this at your plant, follow this 90-day roadmap. Start by baselining your current state, then run a pilot with one component family to create your core passports and scopes. By day 90, you should have your first controlled recovery and be ready to scale the strategy. When talking to management, build a business case that includes all costs, like logistics and inspection, and all value, like reduced lead time and local resilience. We use reliability adjusted value to ensure we aren't ignoring the risk of failure in our calculations. To stay on track, use this 12-point field audit. Only score what you can actually observe or trace. This ensures that your circular maintenance program isn't just a policy on paper, but a reality in the workshop. In summary, circular maintenance is only reliable when the next life is specified, traceable, and verified. I ask for 3 leadership commitments: no critical core without provenance, no repair without a technical scope, and no circular claim without next life evidence. For those who want to dive deeper, here are the key ISO standards and industry reports that inform these practices. These resources provide the formal vocabulary and principles for a circular economy. I'd like to acknowledge the sources of the industrial photography used throughout this presentation. These real-world images help illustrate the complex environments we operate in every day. As we close, I leave you with one action. Next time you see a recovered component, ask yourself, is it really renewed or just repainted? Make the risk visible, make the standard executable, and always verify the result. Thank you.